Every complex machine we rely on, from a jet engine to a power plant, depends on thousands of parts working perfectly. But what happens when they don't? In this explainer, we're going to pull back the curtain and show you how engineers become detectives to figure out why things break. And then we'll dive into the incredible new technology that's being built to predict and stop these failures before they can even start.
So, it all starts with something like this. And no, this is not a special effect from a movie. This is the real-world aftermath of a compressor failure in a massive gas turbine. After nearly 3 years of nonstop operation, one single blade let go and it set off a devastating chain reaction. It just goes to show you, with the power we're dealing with today, even the tiniest, most insignificant-looking crack can lead to absolute catastrophe.
And that brings us to the core challenge, right? The billion-dollar question. In a part that's spinning thousands of times a minute, under insane amounts of stress and heat, how in the world do you find a microscopic flaw that's slowly, silently growing? How do you stop a disaster you can't even see? Well, the answer actually begins after something has already failed. It starts with this fascinating field of engineering forensics. You see, to stop future failures, you first have to become an expert in understanding past ones. Engineers have to learn how to read the story that the broken metal itself is trying to tell them. And here it is. This is the actual blade that failed. Now, to you and me, it might just look like a piece of broken metal, but to an engineer, this is a crime scene. This surface contains a detailed record, a play-by-play of its own destruction. You can even see the two different areas, that smoother part and the rougher section. Those are the first major clues to what went down. Okay, now this is where it gets really, really cool. When you zoom in, you see these incredible curved lines. They're called beach marks, and for good reason. They look exactly like the lines the tide leaves on the sand. Each one of those marks represents a moment in time when the crack grew a little bit, then stopped, then started again. It's literally a timeline of the failure, etched right into the steel. This whole process, this art of metal detective work, it has a name: fractography. It's the science of looking at a fracture and piecing together the entire story of how it broke. We're talking everything from where the crack first kicked off, to the exact path it took, and even how fast it was moving. It is the absolute key to understanding the why behind any failure. And why is this so critical? Well, get this. Research shows that over 80%, yeah, you heard me, 80% of all mechanical failures are caused by one single thing: fatigue. You know how you can bend a paper clip back and forth and it doesn't break at first, but eventually it just snaps? That's fatigue. It's that slow damage from being stressed over and over again. So here's how it all connects on a microscopic level. On the left, you can see that every single stress cycle, every time the engine spools up and down, the crack inches forward just a tiny, tiny bit, and it leaves behind a little mark called a striation. Think of it like a microscopic fingerprint. Now, billions of these tiny fingerprints group together to form those bigger beach marks we can actually see on the right. By measuring how far apart they are, engineers can literally calculate the forces the blade was under and reconstruct its final moments. It's just incredible. Okay, so being a metal detective after the fact is absolutely essential. But the real dream, the ultimate goal, is to stop the failure from ever happening in the first place. And that moves us into the world of proactive systems that engineers use way back in the design phase. One of the absolute cornerstones of this approach is something called FMEA. That stands for Failure Modes and Effects Analysis. My favorite way to describe it is to think of it as a structured, systematic brainstorming session for pessimists. Before they even build anything, engineers get in a room and ask, okay, what are all the possible ways this thing could fail? What happens if it does? And what are we going to do to make sure it doesn't? And this is not some newfangled idea. FMEA is battle-tested. I mean, literally. It was developed by the US military back in the 1940s to make sure their equipment wouldn't fail at the worst possible moment. It was so successful that it eventually got picked up by basically every industry where failure is not an option. We're talking cars, medical devices, you name it. Now, FMEA is really powerful because it forces you to think through every cause and effect. But, it's not perfect. It has its weaknesses. For one, it can be a ton of work, really labor-intensive. And it has a bit of a blind spot when it comes to really complex situations, where maybe 2 or 3 totally separate things fail at once to create a perfect storm. So to get past those limitations, engineering is now taking another massive leap forward.
We're actually moving beyond just proactive prevention and into a whole new world of real-time prediction. And it's all thanks to this amazing concept called the digital twin.
So what in the world is a digital twin? Well, forget about a simple 3D model. This is so much more. Imagine a living, breathing virtual replica of a physical jet engine that exists inside a computer. It is constantly being fed live data from hundreds of sensors on its real-world counterpart, so it perfectly mirrors the exact condition, the exact stresses of the real thing, second by second. But here's the catch. There's a huge computational problem. Running a super detailed simulation to calculate how a crack might grow in a complex part like this is incredibly difficult. A single analysis could take days, even on a supercomputer. And that's pretty useless if you need to know if something's wrong right now. And this is where the magic really happens. Instead of running that whole monster simulation every single time, digital twins use these incredibly efficient, simplified models. These smart models, which are often powered by AI, can take all that live sensor data and forecast the health of the part in real time. Sometimes they can even run faster than real time, predicting a failure hours or even days before it's set to happen. So this is really where we're heading. The future of manufacturing safety and reliability is this incredible fusion of technologies. It's digital twins completely integrated with AI and machine learning. It's better tools so engineering teams can collaborate seamlessly. And it's a much deeper understanding of the human element in all of this. I mean, we are seriously entering an era where our machines might understand their own health better than we do. So it leaves you with a pretty profound question, right? What does our world actually look like when every jet engine, every power plant, every single bridge can predict its own failure long before it ever becomes a catastrophe?